unit right now that is not very math heavy, which for some of you are like, yes, some of you are like, oh, I love the math stuff. Regardless, it is very different from some of the other units we've done, okay? If you love the math part of it and all of the computation, don't worry, there's more of that coming, but not this unit, okay? This is a very conceptual unit. It's also a very vocabulary heavy unit. Does that make sense? So kind of more on the like word stuff as opposed to the mathy stuff. So I just want to let you know that, just because, you know, sometimes having that heads up is helpful, okay? We're going to go through this and just kind of a little bit like Mad Libs, except that they're right answers, okay? And then we'll go do a little field trip benefit to do some of it, and then we'll just kind of do a bit by bit, okay? So here we go. I would direct your attention, if you have not done so already, to the fact that all of this content is in these 3 sections in your book, okay? So if you have not looked at it, there was a lot of stuff in there. I'm sorry, thank you. 15.1, 15.3, and 16.1. This unit of Unit 6 is all about, it's chapters 15 and 16. We will not do it in the order that it is presented in the book because I don't feel like it's a very logical order. I like to do things in the order that makes sense to me, I guess. So hopefully it makes sense to you as well. All right, here we go. So there are 2 fundamental ways to transmit energy or information. We can either transfer matter. So if I wanted to send a message to Morgan, one way I could do that would be to take a piece of paper and I could write a little message. Okay, and then I could ball it up, and then I could transmit this information via matter, right? There you go. And now you get the message, right? So that's one way to do it. Not always the most efficient, though. Are you with me? What's another way that I can transmit this information? Yes, I can beam it. I can yell it out. All of these are forms of waves, right? You're going to send a wave. What did you say? What was the joke? I'm just trying, like, I'm not judging. I'm just trying to, like, kind of put that all together. I'm not sure what that means. All right. Here's the key. So this is like one of those things where it's not just having it filled in. You know, I remember when I was in elementary, middle school, probably even some high school, and like you just had fill the answers in, right? Like, that was the thing. This is really like notes that we're just not doing as like write it all down. So we have to make sure we understand this stuff. Unlike transferring matter, this approach does not result in the permanent displacement of the surroundings. That's really important. So if I write a note to Morgan and I throw it at, like, that piece of paper no longer resides with me, right? Whereas if I just say, hi, I'm communicating, right? I'm transferring information. I'm sending it via a wave. What kind of wave? A sound wave, right? And that sound wave travels through space. No, what is it traveling through? The air, right? And it's displacing those little air molecules. But the air that's right in front of my mouth, it's not like the air in front of my mouth is actually going to her ear. You with me there? Okay. It's being displaced. The wave is traveling. This is weird stuff, you guys. The wave is traveling, but the air is not traveling. It's different. Okay. Energy is being transmitted by the? Yeah. This didn't sound very enthusiastic about that, but we'll write it down. I wonder if it's because you're like, what is that? Well, let's find out. What is the medium? It's the material through which a wave travels. It's temporarily disturbed, right? It gets moved a little. It's not like disturbed, but it's like it moves a little bit, okay? So anytime that I speak or that you speak or that there's any sound, the medium of air is being displaced. It's being disturbed a little bit, and that's how the wave travels. We're talking about sound wave, okay? There are 2 distinct ways in which this disturbance can occur. So this is, here we go. This is like the big stuff. Here we go. All right. If the medium oscillates perpendicular, Whoa, hi. Let's try and make that a little bit smaller. There we go. Oscillates perpendicular to the direction of wave motion. It's called a what kind of wave? Anybody find that one? Transverse. Transverse wave. So if you don't have that written down, get that one written down because that's important. Okay? Okay. How do I remember that transverse waves are ones where that oscillates perpendicular? Transverse starts with a what? A T. The sign for perpendicular is just an upside down T. Yeah? So a transverse wave is one where the medium travels, oscillates perpendicular to the direction of motion. Hey, the word oscillates kind of gives you a clue here. That's why we're doing this unit right now. Okay? The AP curriculum actually puts this at the very end, like we do this like May 3rd or something. It makes sense to do it now because we just did a bunch of oscillation. Now we're just going to look at specific things oscillating. That's what we're doing. Some examples of a transverse wave. Did you see any in your book? Do you know any ideas for that, or should we wait on it? Not yet? Okay, we'll come back to it. We're going to draw a picture in a moment. On the other hand, what's the other kind? What kind of wave? Moves such that the medium moves parallel to the direction of motion. Anybody get that one figured out? Longitudinal. Remember we said that these words are what's important here. Longitudinal starts with a what? Ends with a what? And if you put those two L's together, they look like parallel. With me? Okay. That's how I remember it. It's my little, like, it's not really mnemonic, but it's like kind of a thing like that. All right. We're going to go take a look at what those look like in just a second. In fact, let's go do that right now. Take your papers with you. Okay. We're going to go out in the hall. Field trip to the hall. Field trip. I just felt like that was a little crazy. Let's come back and do this part real quick. We drew a picture. You drew a picture. I just want to make sure your picture looks like my picture. Something like that. Yeah, this is for the transverse wave. Yeah, so the wave is moving like this. But the particles are moving like this. Right? And then after a while, then they start moving back down. Yeah. So the wave particles being disrupted down the medium. Say that one more time. I'm sorry. So the wave is yes. So the particles of the medium are what are being disrupted to transmit the wave. Yes. Actually, I drew my arrows backwards, which is why I started erasing them, and that's why I got distracted. So if the wave is moving this way, these guys are moving up. But these ones are being pulled back down towards their, what is that? The place where they want to be? The equilibrium. Yeah. They're being disrupted. The wave is moving this way, and those particles get pulled, and then they come back down. Right? You can also draw another version of a transverse wave if you have a bunch of them that are going through at a time, like this. This orange one over here would be called a pulse wave. And this one here is a periodic. Periodic means that it's going to keep going and going and going. The disruption is going to happen over and over and over and over. Okay. When you have this periodic wave, you have some other special things here that we're going to get to in just a minute. But we have things called wavelength. We have things called frequency. We have things called amplitude, right? Amplitude is the maximum displacement. We've been talking about that before. That's this right here. Okay. And the wavelength, do we know what the wavelength is? It's a good name, it's a good word. It's pretty descriptive. What is the wavelength? The length of the wave, circular definition there, right? Yeah, yeah. If you flip it over, it's going to tell you that it's the distance the wave travels in a complete cycle. So it's one complete cycle of the wave, how far the wave travels in one cycle, okay? From one point on the wave to another point at the same place in the oscillation. Okay. One more piece here that we're going to add. These places that are up high are often called crests. The crest of the wave. And the place that's down low is sometimes called the trough. I don't use this terminology a lot. Really, the reason that I'm doing it is to show you that the word trough is spelled funny. It's hard, like a lot of people have a hard time, like even very intelligent people that can read like T-R-O-U-G-H, it's weird. So anyway, crest and trough. So if you see that terminology, that's what they're talking about. That would be a negative amplitude. Okay. What kinds of waves travel as transverse waves? You saw one out in the hallway. Yeah, a wave on a spring can be transverse. Have you experienced any other waves that are transverse waves? Have you ever seen anything that looks like that goes up and down and up and down? Yeah. Yeah, like the ropes. Yeah, yeah, yeah. So wave on a spring, wave on a rope. You can make a transverse wave with lots of different things. Absolutely, absolutely. You ever seen any in nature? What was that? You go like this? What happens in your water bottle? Do you get some transverse waves on the surface of a water? Yeah. Surface water waves. Have you ever dropped a pebble into a pond or something like that? Okay. Skipped a stone. All of these things generate transverse waves. Before you come to class tomorrow, I want you to look up other examples of transverse waves. Put that on your list of things to do. Okay? Do it. I mean it. Do it. All right. Don't look at me like, yeah, sure, I'm going to do it, Carveling. Like, I mean, actually do it. All right. Longitudinal. Draw a sketch. So we can totally draw this sketch. Oops. I don't want to make it smaller. So it's spread out, and then it's going to get really squished together. And then it's going to get spread out, and then it's going to get really squished together. And then it's going to get spread out again. Okay? That is a a longitudinal wave. Okay. Trying to draw pictures that make it kind of similar in setup to these ones here. The wave motion goes like this. What direction do the particles move in? Friends, I feel like there's a lot of conversation here that's, I'm going to be honest, just completely distracting to me. I'm not saying that you are or are not able to pay attention, but I am distracted from what I'm trying to do. So please minimize that. What direction are the particles moving in? So tell me, in this direction, are they moving right and left, up and down, at a diagonal? What are they doing? They're moving to the right or left? Yeah. Do they move just one way? One way at a time? Yes. But they will oscillate back and forth, right? That's the whole idea. Yeah, so the particles are going to move like this, and then they'll move back like this. Yeah. So the particles themselves are going to move parallel to the wave motion. I just want to make sure that's really in your head. It's kind of weird because usually when we start talking about waves, you know, when you're talking about waves like this, but this kind of a little bit less intuitive. We can see this periodic motion in this thing as well, okay? You can find a wavelength from one squishy part to another. And indeed, it may surprise you that squishy part is not a technical term, and that there are actually technical terms for this. Does anybody know what the one is for when they're squished together? Starts with a C. It is a compression. The place where they are spread apart really, really far has a less common name. It starts with an R. Rarefaction. It's kind of an ugly name, I think, but that's what it is. So the compression is a spot of very high density. So if you think about it in terms of the spring, those coils are really, really close together in a compression. And at a rarefaction, they're very, very spread out, okay? So compression is high density. And rarefaction is low density. Have you ever seen any examples of a longitudinal wave? What's that? Worm. Yeah. I've been teaching this for a long time and no one has ever brought that up. But yeah, like when worms move, they absolutely use something like longitudinal wave motion. I like that. Hold on just a second. That's worm motion. Now, and what did you say, Chris? Okay. You guys are 2 for 2 in things that I've never, ever heard before. It's kind of impressive. Pinball machine. I don't know what that says about you all, but it is interesting. Yes, worm motion, pinball. So in both of these cases, I would say in the pinball machine, that would be like a pulse wave, right? And it's kind of like, because it's not going to go back and forth and back and forth and back and forth and back and forth. And in worm motion, I mean, when you start getting into biomechanics, it's kind of funny because whether it's actually a wave or whether it's just that the motion looks kind of like that, I could see debates on both sides, but I like it. I'm going to leave it up there. Is that okay? Yeah. An accordion? So same kind of thing. I would call that like a pulse. Yeah, but in doing that, as you give it that pressure, what else is being compressed besides just the accordion itself? Do you know? I don't know a lot about accordions either. Although I did have a roommate in college who played the accordion at like 9 a.m. on Sunday morning in the apartment. Not my favorite person at 9 a.m. on Sunday morning. Don't do that when you go to college. No, you will not make friends. Wait, don't play the accordion at 9 a.m. on Sunday morning. Like, just don't do it. The air is getting compressed. Yeah, yeah. Which is, I mean, that is true. Yeah. All right. Anything else? Have you ever seen any other ones? Or heard any other ones? Mm-hmm. Yes? Yeah! They're the #1 most well-known of all longitudinal waves, the sound wave. Absolutely. In fact, I even went to get my tuning forks today. It's so cool. Sound waves, yeah, have you guys seen tuning forks before? Welcome to a tuning fork. It's kind of a funny looking device, but it has a little number on there. Jason, give yourself the number sign. 256C. What does the 256C mean? Anybody know? 256 hertz. That is the frequency with which this is manufactured to oscillate. Okay, so I'm going to give a little push, and then if you look very carefully, yeah, yeah, it's moving back and forth really, really fast. How fast is it moving back and forth and back and forth? 256 times every second. Every second it moves back and forth 256 times. What? What's that? The C is pitch, middle C. Yeah, yeah. Ding. It's middle C. If you play it on piano, it is. Bing. So that's 256 times every second that those things are moving back and forth. Okay? And the fact that the tuning fork is moving, it doesn't make the sound. How do we hear it? Yeah, it pushes the air molecules that are sitting right here back and forth. How often? 256 times every second. Are you with me there? And so those little air molecules get pushed 256 times every second, and they go to your eardrum, and they make your eardrum oscillate 256 times every second. That is the sound wave. Yeah, yeah, it is. Do you not believe me in this moment? Is that blowing your mind?
No.
Oh, you just seem super excited about it. I love it. Yeah, yeah. So, describe for me how you do that. Like, what do you do to tune your? Because I don't play the violin.
Well, we use like that.
Right, but one could, right?
Yeah.
Okay, and so if you used a, like, describe the process for those of us that don't code. Uh-huh. 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 Yeah, exactly. Yeah. And so you can actually, it's pretty amazing. So this is the weird thing. So you have the electronic one, right? That just kind of measures the frequency of the sound. Is that right?
It just plays.
Okay, so you can kind of like hear it and tell. Yeah. So here's the weird thing. Back in the day, when they were tuning pianos, before they had the electronic, because they've been tuning pianos for a long time, right, hundreds of years. The way you actually were able to tell is that the piano tuner would come with a set of tuning forks, and they hit a note, and like on the piano, and then they put the tuning fork right next to it, and it would actually cause the tuning fork to vibrate at the right frequency if the string was tightened to the right amount. So it actually made, I think it blows my mind, because instead of like striking the tuning fork, the string would actually vibrate the air and cause this thing to vibrate.
Let's sing a perfect little C so it vibrates yourself.
Who's got that one? Who's got perfect pitch?
On the saxophone.
There you go. So you can bring your saxophone and we can try it out. I don't know. I've never actually seen it happen, but I've heard about it happening. Heard about it happening? Right? Did you catch that? I'm glad. Thank you for that. What's that? What were you excited about? Yeah. I had a student, I don't know, like 8 years ago that was like amazing. Like she could just do it. Yeah. We don't have time for that. I like that. Why would I? What's the point? All right. Since we're in here, we may go back outside tomorrow. We'll see. Since we're in here, let's keep doing this real quick. When sending information via a particle or wave, the transmission is not instantaneous. Okay? Instantaneous isn't a thing, like it doesn't happen. I love sci-fi, but it's not actually possible in physics as we know it right now. Okay? The velocity of a wave can be expressed with this equation. This is like one of maybe 2 equations that you'll see this unit. And I think the other, maybe not even, maybe this is it. I can't remember. I can look, I guess. Let me take a peek. Oh, that's probably it. And actually, it says waves. The whole section on waves has just this equation. So there you go. Now you know all of the equations for the entire unit right there. And it's an easy equation. We just got to figure out what it means. So here is the equation itself. The velocity of the wave is v, right? That kind of makes sense. That seems to correspond to what we've talked about before. What's this thing? Lambda. Lambda is the way with Roman letters that one would spell the Greek letter lambda. Lambda is right up there next to kappa and mu. Okay? This is little lambda. Lambda represents blank, the distance a wave travels in a complete cycle. You know what that is now? What is it? Wavelength. Okay? And is measured in distance. What's distance measured in, friends? Meters. T is the period. What's period? Time for one cycle. It's the same period that we've been talking about before. That's why we're doing this right after last unit, right? Because it's all the same stuff. We're just applying all the simple harmonic motion terms and stuff that we know to this, okay? Alternately, velocity can be written as lambda times frequency. Hopefully that makes sense to you, given that we know that frequency and period are inverse, right? Okay, so they didn't write this one down on the equation sheet, but you know that period and frequency are inverse, so it should be easy enough. Okay, we started doing this, we got distracted because we were trying to watch waves go, so let's just make sure we've got this all here. So unlike matter, waves can indeed occupy the same space at the same time. When two waves meet, they undergo this thing called superposition. If you haven't underlined or highlighted or whatever that word, I would definitely do so. It's a big one. We'll talk about it tomorrow or Monday, I can't remember. In which the total amplitude of two or more waves in the same space is the blank of their individual amplitude. So this is what we started with, and then we were about to get run over, so we, came back inside. So if we have one wave that comes up like this, going this way, and we have another wave that's down like this, oops. What do we think happens to those two waves? What do they do? They do cancel. They cancel. So if this one had an amplitude of, let's say, 6 centimeters, and this one has an amplitude of -6 centimeters, the amplitude at that moment when they cross is 0. The amplitude of two more waves in the same space is the blank of their individual amplitudes. Yep. It is important to note that the combination, also known as interference, only occurs for an instant, and then the waves continue to travel. That's a big deal. If Morgan and I both decided to send information to each other, right? And so I wrote a little note on a piece of paper, and she wrote a little note on a piece of paper, and we both had good aim, which, I mean, I don't know about you, but and we threw them, they might bounce off of each other. You with me there, right? And so then neither of us would get any information. But if she sits down and like, hey, how's it going? And she's like, hey, how's it going? And we say it at the same time, we both can hear that information, because even if those waves occupy the same space for the same moment, they just keep going, right? That's a pretty big deal. Waves are kind of amazing like that. They're very like indestructible in that way, okay? Generally, we can separate the phenomenon into two types. One, when the disturbances are on the same side of equilibrium, resulting in an increase in amplitude. What do we call that? Constructive interference. And the other one, we can write an opposite. Destructive is going to be when the disturbances are on, anybody? Yeah. Sometimes we differentiate between completely destructive and just partially destructive. If you have two things that have the same amplitude, it'll be completely destructive. If one's bigger than the other, it's just going to be partially destructive. We're going to do a lab tomorrow, you guys. I will see you then. Make sure that you have a computer or you know somebody that does, right? We need to have some computers tomorrow. So.